So it's 3 o'clock on my machine. So people are still dropping in. We have 13 persons right now. Maybe I can start with a bit of introduction, and then we also give Simone a couple of minutes, and also that all the people have time to drop in. So welcome to this session, very mixed signal related session P3.4, 3.5, and 3.6. They will be 30 minutes each. So I think that it will be a story about 25 minutes and then 5 minutes for Q&A. Yeah, then we will start with session 3.4, and it will be presented by Simone Fontanesi. He graduated in electrical engineering at the University of Pisa in 2015. During his studies, he made experiences in the US, UK, Germany, and after his master thesis at Bosch, he joined Infineon Technologies, Austria, in Villach. Since 4 years, he works now as a product definition and application engineer for automotive magnetic sensors. And I would like to give the floor to you, Simone. And I don't hear you.
Right. I guess now you hear me. So thanks for the introduction. And now I'm going to share my screen. And okay, I suppose you see the title page, right?
It looks good, yes.
So should I start?
Please start.
Okay, so hello everyone. My name is Simone Fontanesi, and today, together with Paul Ehrlich, who co-authored this paper, I'm going to share with you an experience that we accumulated in the past few years about comparison of different methodologies to simulate mixed signal IC. As introduced, I'm working in Infineon, and I co-authored the paper together with Paul, Karsten, Einwich from COSEDA technology, and 2 other colleagues from Infineon, Gaetano, Formato, and Andrea, Possemato. So first of all, I'm going to introduce the applications and the use case that we benchmarked with different approaches. I think this is important because, as you will see, different methods are good or bad depending on the use case on ends. Then, together with Paul, I'm going to share the 4 different approaches that we evaluated and share with you the simulation results, and finally conclude summing up the pros and cons of these 4 approaches, and also giving an outlook of what we plan to use in our department. So the department I work in, it's called Sense and Control, and is a subdivision of automotive. So what we develop is magnetic sensors for automotive application. And in particular, the group I'm working in, we are responsible to define the requirements for the next generation products. So on the V model that you see on the right, we are at this level. So we define the product requirements, which usually comes directly from customers or from the market or from our application assumption. And these documents is then used by the concept engineer and by the lead designers in order to define the hardware and software requirements which are used for the implementation of the functionality on the silicon. Along the development process, we use virtual prototyping, so model of our product and the model of our system, in order to assess the feasibility of these requirements, and in order to build the proper architecture that fulfills this requirement. And this model is refined along the V process, adding more and more details and moving from high-level languages like System C, AMS, to more hardware-friendly language like VHDL or Verilog. And then what we do is we use this model in the test cases from the application to see if the behavior of the device is as expected. So the magnetic sensor that we developed are used in a wide range of applications. Here I just name a few. In general, they measure a physical quantity. This could be rotational angle, linear position, or speed of something that it's rotating. Or it could be the current that is flowing in a conductor. And the magnetic field can be, let's say, this physical quantity can be made proportional to a magnetic field, for example, by using a magnetic encoder. And what our sensors are doing is to sense this magnetic field that is generated by the mechanical part that it's rotating or moving. And then we process this signal and provide the information to the microcontroller, to the ECU. So here an example of what a speed sensor does. There is a magnetic field which is proportional to the rotational speed of a certain target wheel. This magnetic field is converted into voltage, and then the sensor communicates with the ECU with a digital protocol that is proportional to the speed of rotation. In particular, to benchmark these 4 simulation approaches, we have been using a magnetic speed sensor, which has an architecture as depicted in this picture. So there are 3 channels, which consist of sensing element based on TMR technology, analog signal processing with preamplifier and filters, analog to digital converters, and then some digital algorithm implemented in VHDL, which process the input coming from the analog front end and which communicate then the data to the ECU. So this is clearly a mixed signal environment. And as you will see, we have been used languages that are suitable for this kind of systems. So the 4 simulation approaches that we have compared in this work are shown at high level in this slide. And then Paul and I will go into details of each of these approaches. So the approach number 1 and number 4 are purely virtual, in the sense that everything happens in software in a virtual environment. And the test bench and the stimuli checker, so for the pass-fail criteria, as well as the DUT analog part, are implemented in System C AMS language. And the digital part is written in VHDL and also simulated with a VHDL simulator. For approach number 2 and approach number 3, these are hybrid approaches, because you see the FPGA comes into the game, and also system on chip. Basically, what is in blue in approach number 2 and approach number 3 is running on real hardware. And as you can see, for the approach number 2, the test bench and the DUT are fully synthesized on a FPGA. Instead, for approach number 3, the digital part is synthesized on an FPGA, and the remaining analog part and test bench is running on an ARM processor. And for both approaches, we use the same platform, which is based on a ZenQ 7000 system on chip. So the approach number 1 is what we start from a few years ago in our department, and has been used in order to benchmark the other 3 approaches in terms of simulation speed and effort needed in order to reach a certain result. And as you can see on the left, the flow starts by implementing the model of our product as well as the test bench in System C, and then run the regression in System C based environment using System C kernel. And then later on during the development process, once the design is starting and the VHDL is available, we simply replace the high-level digital model with the VHDL description, and we use Cadence as a simulation kernel. And as you can see on the bottom picture, we have the capability also to co-simulate the two models so that we can cross-validate the VHDL against our golden reference of system C, and then check, given the same input stimuli, if the output shapes of the two description are matching. As I said, this was where we started from some years ago. And then in order to speed up the simulation, we started to analyze different approaches. Last year, we presented at DVCon together with some colleagues an approach which was based on system on chip, in particular on FPGA. At that time, we reused an hardware platform which we were using to provide the fast prototype to our customers. So this platform of hardware prototyping consists of a so-called snickerdoodle FPGA board. This is commercially available and implemented ZinQ 7000 system on chip. And then we were developing an analog front-end board to attach on top, as well as the sensing element board. So this board can work in a real application environment and have been also shared with customers. And then for this approach, we reused the system on chip in this way. So we implemented everything from the from the DUT digital part and the analog front end up to the test bench and the test bench control inside the FPGA. So in this case, everything was written in a synthesizable manner, including the test bench. And the host PC was basically interacting with the FPGA in order to start and stop the simulation and assess the results. This approach was pretty fast on a single simulation, but was suffering due to the continuous communication between the FPGA and the host PC, and later Paul will go into more details. Now, Paul, if you want to continue.
Yeah, can you hear me?
Yeah.
Okay. So approach number 3, then we sort, can we reuse more of the system level model from the number 1, so we don't have to synthesize as much as we did in approach number 2. And then therefore we started with an hardware in the loop approach. Actually, it is not a hardware in the loop approach since we have no hardware in the loop, since only we use the FPGA. And we are going to put the digital part, which was simulated with the Cadence simulator, into the FPGA, and downstream it there with the Xilinx flow into a bitstream down to the FPGA. And we will leave the remaining system model as a system CMS and place it in the processor. This approach was developed earlier, so we had it available. If you were more interested in this, you should listen to the next talk of Martin Barnasconi in this session as well. So we use the libraries that COSEDA provides to compile the test bench for the ARM processor. And it also provides decoupling to the FPGA, so it does the data and the time synchronization to the digital part. Simone, if you can go to the next slide. In this case, we used a Z board as a Sync 7000 device. In a difference to the snickerdoodle, it has a little bit slower processor, but a bigger FPGA. And it has, as a difference we needed, is an Ethernet controller. So we can control the simulation from a lab computer. The Sync Z board in that case has only a 666 megahertz processor and 58,000 logic cell FPGA, which is quite large enough to fit the digital part here. The SD card is used with an Linux system, so it provides the base layer for the system C to run on, and it also allows the coupling to the lab computer and the storing of trace files on the SD card. This approach turned out to be slow, but I will say more on that on results later on. And then we come to approach number 4. We sort, can we do something without hardware and speed up the simulation we got from approach number 1? And the simple thing to do is do parallelization. And the problems with parallelization is, can we have multiple Verilog simulator kernels running in parallel without running in licensing issues and without interference between each other? So what we found is, which was capable of doing that, was the XSI simulator from Xilinx. It has a C interface, so we can control it from system C. Every use case, so we are running thousands of use cases, is getting its own thread and runs against its own XSI simulator. And therefore we can spawn an arbitrary number of simulations in parallel, only depending on the number of CPUs our server machine will have. So Simone will say something about the use case, and then I will go over to the deeper results, what the different approaches showed.
Exactly. So to compare the 4 approaches, we took out of the, let's say, normally available 10 of the use cases that we simulate in a regression-like approach. We took 2 examples. One is forward rotation, so means the car is moving forward and never stopping in this case. And this is depicted on the left. And the other example, it's a rotational vibration, so where the car is moving, then stopping. And here we make the mechanical vibration start, and then the car moves again. And we are interested in the evaluation of the output protocol from our sensor, which, as you can see in this case, is able to suppress the vibrations. And for these use cases, we normally have different simulation input parameters that we can change. For instance, the rotational frequency, so the speed at which the wheel is rotating, the starting phase of this wheel, the air gap, which is the distance between the sensor and the target wheel, and so on and so forth. And you can imagine that if you increase this number of simulation parameter, the total number of simulation increase pretty fast. So for just these 2 use cases, we had more than 12,000 simulation. And that is why we are very interested in speeding up the simulation as much as we can.
Okay, so approach number 1, set the floor, was the first one available. For the first use case, you can see down here, I'm not sure if you're able to see my mouse, probably not, since it's Simone's presentation. So forward rotation showed to have up 250 runs in 1 hour. And if you do the rotational 12,500, the benchmark then is the 54 hours it took to do all the 12,500 runs here. So simulation number 2 then had 13.5 hours to run the same speed or the same amount of data, so it was faster. And there's a theoretical speed as well, which is down 18 minutes, which is pretty fast. This was never reached because between the runs, so this is when the FPGA is actually doing calculations, but in between, the FPGA has to be reconfigured and traces has to be retrieved again. And this was done via Xilinx USB, which is probably not the best way to do it. So there might be potential for this approach as well, to get down to these 18 minutes, but not now yet. So it is faster, but the downside is that we had to convert the whole model to be synthesizable. And from this point on, the models are kind of out of sync and not coupled anymore. So you have to manually keep them in sync. If you change something on one side, then you have to update the model, or the other way around. if you find something in the RTL and then you want to go back to system model, then you have to find it there. So we come to approach number 3. It had the benefit that it did directly run, so we were able to reuse the system C as it is and compile it for the ARM platform. It coupled nicely to desynthesized bitstream and was able to run the test cases there. The problem is, as you see, we only did the forward rotation with 250 runs. It already took 4 hours and 50 minutes. This is mainly due to the slow speed of the ARM A9 processor. Even offloading the heavily digital part into the FPGA let the remaining system load on the ARM as high as it is. So if you do a calculation back of an envelope, you would see that the 666 megahertz of the Z board compared to a full-blown x86 server processor, which has a frequency around 4 gigahertz and maybe the beta architecture as well, is already a factor 6 to 7. So we are not factor 6 to 7 slower now. This shows that the digital part was offloaded, otherwise it would not reach that speed. But for this use case, the test bench, which is also doing a lot of the testing there and evaluation of the signals, is too heavy load for the ARM processor. So this approach can be nicely used, but only if you have a really lightweight test bench to run on and leave the ARM more time to idle. So the Snickerdoodle has 800 megahertz. That would relieve only a little. So, and even the higher sync devices only scale up to 1 gigahertz or something over that. But still, with this use case, this wouldn't help a lot. So we were looking for a speed up and not so much for like a comparable result. And approach number 2, as expected, it has the slowest the shortest time on simulation. We used a 32 core machine here. If you compare the resulting 4 hours and 30 minutes, 37 minutes to the 50 hours originally, you see that the speed up is a factor of 12. So we investigated that further to see how we did with how we would do with our different core numbers. And you see with the 32 cores, we are already in some kind of saturation. It doesn't scale that much anymore. And we looked deeper in why it is not scaling anymore. And we figured out different things where this happens. And this is the simulation offloading via LSF to the server farm is taking a constant time, and it is always done. And it also does the configuration and copying the parameter files and results files forth and back between the servers. And this only depends on the bandwidth, not on the number of CPU cores you have. And as then the threads are going to run in parallel, then they have their own CPU, but they still share hardware I/O and other I/O stuff like the cache. So for tracing, they will block each other. So 32 cores only a slight increase then to 16, for example. Yeah, another option would be if you split the 12,500 in like 2 blocks and offload them to 2 different machines. But this is like an outlook for the future, since the 4 hours and 30 minutes here for regression one were fair enough fast. So now it's able to return results more quickly than waiting more than 2 days. So we would come to a conclusion between the 4 approaches. So the first one was the benchmark. It has the most powerful Verilog simulator with cadence available. It's fine to use. Approach number 2 was pretty fast. It probably has still some potential with the configuration. Has the downside that the models get kind of out of sync because you synthesize down the analog stuff in a synthesizable way. Approach number 3 is valid. It's easy to use, but you have to have a digital heavy design and or maybe in the future more powerful system on chip boards which have a higher processor power. I mean, the FPGA was utilized like 20%, so we still have a lot of FPGA space left, but we need more processing power for the system C world to run as well. And approach number 4, easy to implement as well. It's currently the preferred approach for Infineon for the magnetic sensors, and it scales with the processors. It still has potential if you split over different machines, and you probably can also do it with other simulators. You only have to make sure that they are license free for the multi-threading and are easily controllable with C or C++ interface from System C. Thanks everybody for your attention. So it looks like we close in time.
Yeah.
Yeah, it looks very good. So we have a couple of minutes left for Q&A. But maybe before doing that, I also would like to say, let's say, express a word of thanks. So thanks, Paul. Thanks, Simone. I think it was very interesting. And I think that it's time for you to get some questions. So please shoot. Nobody? Okay, in that case, yeah, so I was wondering myself a bit. It's a very nice comparison. And I would like to, let's say, to have some kind of guidelines. And actually, I was thinking about when it is feasible in relation to sample times and let's say the time constants of analog signals. Because I can imagine that this approach works very well in this case for magnetic sensors in Infineon. But where does the approach really stop? Is it also suitable for RF systems, for example?
So, Paul, maybe please correct me, but I would say that approach 4 can be suitable for any kind of system, or?
Yes.
Because this is purely virtual. So
COSEDA provides you an coupling interface for every, if you have a module which only has System C and System C interface, you can right click on the model and then generate the wrapper, and this is included in your schematic, and you can place your RF system around it. So if you have any digital stuff you want to offload to an XSI simulator, then yes. But I think you were maybe asking about a different approach to setboard stuff, or?
Oh yeah, so I'm just curious if we should even consider that. So I understand indeed you have the schematic, you have the wrapper, you have, let's say, simulators. I have to admit, if I look at our own situation, that we are looking at commercial simulators, so the big three basically. But I understand for you that also in the simulator choice that there is that we have to go out of our box at least. So because we are not an Xilinx user actually.
Yeah, sure. You can, if you have a different simulator, then if it's coupling able. But I think if you're going to if you want to like use the setboard approach in RF, then the AMS is probably killing the performance on the processor as well, similar like in this use case. Because it is quite the AMS calculations are quite heavy, so I'm not sure if you have enough digital power to offload to the Verilog FPGA. Yeah, and analog stuff is also for approach number 2. I'm not sure. Then Simone is probably more the expert. If you can synthesize your analog stuff to totally to the FPGA.
So for the approach number 2, as I said, everything was synthesized to the FPGA, and the approach used was the following. For the analog parts, maybe I go back to that slide. So for this is our device under test, which means the magnetic sensor, and everything from the digital core to the analog front end was synthesized on the FPGA. In particular, the approach that we used was to use some automatic conversion tool from Python to synthesizable system Verilog. This was developed by some of the co-author of the paper and in collaboration also with Stanford University. And let's say this is a nice approach if you start from the beginning to develop your model in Python. This was not fitting so well with our department methodology, because usually at application and concept level, we are used to use system CIMS. So for us was extra effort, but in case you are open to start from Python, I have to say this approach was quite nice. And then this means you could have your digital core from the design in VHDL or Verilog. You could have your analog front end, let's say, synthesized from a high-level language, and what was left then is the test bench. And for this, let's say, theoretical study for the paper of last year, we implemented a simple sine wave generator in Verilog. And then we were providing different simulation settings from a script which was hosted on the main PC, written in Python. And for this reason, you saw let's say the results that we achieved were good, but not as good as they could be. So if we would have implemented also the intelligence, not on the host PC, but directly in the FPGA, I think we would have achieved something like this. So in case you put everything on the FPGA, probably this is the fastest approach, but of course it's the one who require more effort from implementation point of view. I hope I answered the question.
Yeah, so I'm really happy with your answer. So it was really insightful. So thanks.
Okay, thank you.
Also have a look at the time. I think that it's also time to move on. So once again, thank you very much, Paul. Thank you very much, Simone. I really enjoyed it. And then we will go to the next presentation. And the next presentation, it's about unified model hardware in loop methodology for mixed signal system design. Martin Barnasconi will do the presentation. Will talk. Martin, it's a pleasure to have you here. I don't think that you need much introduction. So please start.
Yeah, let me see if I can share my screen. Is it visible?
Yes, it's.
Yes.
I can hear you.
And I think we have Paul as well, and perhaps Karsten as well, because they also did help us with this flow and implementation. So good to have them on board. So thanks for the introduction. My name is Martin Barnasconi, working in NXP Semiconductors. This paper is made with many people. Will Kitzen and Thieu Lammers from the NXP organization, both located in Eindhoven. All the three of us are in Eindhoven. And this work has been established in close collaboration with COSEDA Technologies in Germany. Paul and Karsten. Paul was also involved in the previous talk, and you might even see similar technologies, but the good news is a different flow and a different methodology, and which we will explain to you in the coming 20-25 minutes.
The real hardware in the loop.
Exactly. That was a spoiler, right? Okay, so outline for this today, a bit on the goals, why we are doing this, and why we are looking into what we call a unified model hardware in the loop flow. I think this is the approach to do things in a loop is not new. There is a model in the loop already for quite some time. Hardware in the loop also exists for quite a while. We will explain what the differences are and why we have chosen a unified model / hardware in the loop flow. We will look in related work, especially what is done in other industries and which approaches are applied there. And we explain the differences between what we do. Then we will dive into the methodology and flow itself. The interesting piece of this talk is that this is targeting a mixed signal application. The discussions on the use of emulation and FPGA very often address digital hardware, digital IP. This is a demanding mixed signal application, which makes it more demanding and more challenging. Still, it's mixed signal, so there is some digital involved, meaning that we can do some high-level synthesis as well to map things on the FPGA. And we use, as a starting point, we try to apply a top-down design flow. We will say something about, okay, the use of System C and System C AMS. We did demonstrate this flow, so we will zoom into the demonstrator. We also used for the hardware and application side the Z board. And we will show some measurements and results and draw some conclusions and summary, obviously. Okay, what are the goals of this exercise is that first of all, we like to have a design flow from, I would say, idea to implementation, which is much more efficient. So how can we increase the design productivity and efficiency? And what we see, if you follow a traditional development cycle, you see that design and verification is a bit decoupled. They are also decoupled from a tooling perspective, but also in time, they are decoupled. So we really like to get that much more closer together, that the design and verification and even hardware prototyping, so bringing things to the lab, that is getting more unified and more seamless. So the second bullet, by doing so, we should really be able to do early verification and validation. Very often the verification teams are looking into the functional verifications at an abstract level. In the AMS domain, it is known that just pure functionality is not enough. You really also need to look at performance and corner cases of your mixed signal application. So if you can already do validation as well in simulation, but also repeat that exercise in the hardware world, that would be really beneficial. So the verification and validation holds both at the left side of the V model as well as the right side of the V model. And here we really like to have a hybrid of using system simulation technology combined with technologies available in the prototyping domain. And the last item is on, okay, if we do validation, you want to look at real life scenarios. This is really what validation is about, right? It's verification is often, okay, am I designing the product in the right manner? But you want to validate if you're really meeting the application specific scenarios. And real life scenarios often means that you really need to look at real-time signals. And we all know that analog simulations are far away from real-time execution. So bringing some of the simulation models into the lab has an additional challenging constraint that this should all run in real time. Because if you do not meet your real-time constraints, then the whole thing is actually not running in the lab. And I said already, the special focus is on the mixed signal application domain. So specification-wise and the multi-domain nature of mixed signal makes it a very interesting application domain. And let's see if some technologies we are selecting are also suitable for mixed signal applications. Okay, let's zoom in a bit on the different hardware in the loop approaches, model in the loop, hardware in the loop, and what we call the unified model in the loop flow. At the left, you see the traditional simulation-centric model in the loop flow, where both the DUT and the application itself are running in simulation. Can be multiple simulators coupled together, but this is all happening in the simulation. So often rather straightforward to do. It's already getting more challenging if you want to combine hardware implementations of your DUT together with simulation model, the traditional hardware in the loop, which is well exercised in the automotive domain. And in this picture, we show that the DUT is a hardware implementation, but it can also be the other way around, that the application environment is hardware and the DUT is a software model. But the combination of hardware software is often a challenge because these are rather separated systems, and often the communication between the different environments might be a bottleneck, making sure that the data arrives in time and that there are no latency when it comes to coupling the two frameworks together. What we are looking for, we want to go one step further, what we call the unified model and hardware in the loop approach, where we actually, for both the design and the test as well as the application, we like to leverage the available technology and even use simulation in a hardware context or the other way around, and the same with the physical environment. So the technology today available where we have processors and FPGAs in a single die or on a single board allows us to go this route into a unified model hardware in the loop flow. Some related work, I think here COSEDA has done already quite some years, some studies and gained a lot of knowledge. So I hand over to Paul to give an overview on the related work activities.
As Morten said, hardware in the loop is was heavily used in the automotive industry, Tier 1 OEM. The typical Hill systems there are D-space systems working together with MATLAB. They put whole ECUs with firmware in the loop, and then they simulate the environment around this hardware piece. And it is not really centric to the chip design we would like to have, since we want to have not only have digital functionality around our ECU, but we want to have analogs as well. So for our upcoming flow, we are looking for something to simulate a system CMS as a whole. In the upper right picture, you can see how such a D-space system basically is composed of. So you have a link board to the process, to control computer, and a processor board where your application runs on x86 machine, and then you have I/O boards to connect to the ECU where you're going to test. And yeah, and they in the hardware in the automotive industry, they use it to do firmware development, for example. So the firmware developer has his processor as a whole hardware piece and puts down his firmware, and then he wants to see how the ECU behaves in a failure environment or in a normal environment, for example. Yeah. So this is where hardware in the loop is probably mainly coming from, and we want to use it for circuit design as well. So I will give back to Martin.
Okay, thanks, Paul. Yeah, so the related work shows that this is known technology, but you've also seen that the type of devices and racks available and the hardware and the pricing for this hardware is not something I can easily introduce in a lab environment. I need to convince a few managers and putting a few $1,000 on the table to get such a framework up and running. So for a prototype, that was not really realistic. So we will come to we did come to an approach which is much more cost effective. So we will zoom into that in a few slides later. Let's first have a look at the design methodology and flow. We start, since we do a top-down design flow, we start the creation of the system of the device under test in a abstract way using System C and System C AMS. Obviously, System C for the digital part and System C AMS describing the analog mixed signal part of the system. The digital part can be synthesized or even code-generated, but there are different, depends a bit on the type of circuit, but we have used high-level synthesis And of course, then we, from the RTL, we go to a traditional logic synthesis flow to map the functionality on the FPGA. So that is basically the right part in this gray picture. From the digital flow follows the high-level synthesis to RTL to logic synthesis. For the analog mixed signal elements in the system, we follow a different approach where we actually leverage a CPU, which is part of the board. And in our case, this is an ARM processor, which means we need to run System C AMS on the ARM processor and deal with some of the constraints and capabilities of that platform. We will come to that in a minute. And then having then the mixed signal part as well as the digital, we can basically combine that, that it comes together on a prototyping board where we actually have the demanding requirements that we want to really run this real time. And it's also in a closed loop, which I will show in an application diagram. And in that sense, this was the proof of concept to see if such an approach actually works in a real application domain. So let's zoom into the different elements which I showed on the previous slide. So let's start with the DOT itself. This is a mixed signal power electronics application. So we're talking here about elements which are part of your supply unit of your laptop, for example, which consists of a flyback converter, which is the external hardware, and it's controlled by a so-called flyback controller IC, which is in our case the device under test. So you see that here in the picture, we have our DOT, the flyback controller, containing some digital parts, and we like to map that on the FPGA, and the flyback controller contains, the digital part maps on the FPGA, and the analog functionality, of course, we cannot map that on the FPGA. There are attempts to look into real number modeling on FPGA, but I'm not really convinced that that is the right approach. Instead, we use the CPU, and we basically can run some sort of lightweight simulation to simulate the analog circuitry, and even the solvers we run on the embedded processor. In the picture below, you see a bit more detailed diagram where you see the application diagram with the transformer, with the primary and secondary side. And you see again the DOT, which is sensing the output and making sure with the electronics, both the analog and digital, that the circuit is that there is a correct control mechanism. So we are basically leveraging the CPU technology and the FPGA to map things from the DUT onto this hardware platform. High-level synthesis and logic synthesis is used for the digital blocks. I already mentioned that, and there the exercise is that when the circuits, the System C models are developed at a higher abstraction level, we need to make sure that these can be synthesized following the Accelera synthesizable subset, using the correct syntax, as well as that we are moving from a floating point to fixed point notation, obviously. The good news is that the COSEDA tools gives a lot of support how to do this flow. There are scripts available to generate the relevant scripts, and there is a seamless interface with, for instance, the Siemens Catapult HLS tool flow. And I think there are also papers on that written. So if you want to know more about that, I refer to the references in the paper. As said, the RTL, which comes out of the HLS flow, will go then into a traditional logic synthesis flow. And for that, we used Xilinx Vivado tools for that.
So I will take over. I want to give some insights on the stepstones you have to take when you're going to use System C AMS on an ARM-based platform or on an other processor, for example, as well. So AMS is heavily floating point heavy, so you better make use of your floating point unit of the processor if you have one. So typically there's a neon or whatever a floating point available. When you use System C on a different processor, you have a look at the system C threading. So system C doesn't run in parallel, but it is using threads. And if you don't implement them by your own for an assembler for ARM, it will map them to system threads. And system threads are way, way slower than implementing them in the assembler by your own. So under Linux, it is called Quick Thread Library, and you have to have your assembler ready for the ARM in this case. We used as a second big point, we used a real-time application system. I mean, bare metal running system C is possible, but it doesn't make sense because you probably gain like 10% more, but you have a little bit way more struggle because system C has an OS dependency to memory management and stuff like that. And if you want to store traces, you want to have a file system as well. And all this is provided if you go with an operating system. If you go for an operating system, make sure it's preemptive. This means if a system thread gets executed, it has to be interruptible as much as possible, because you want to have a precise return time for your threads running the simulation, because if they don't do the calculations in time, your hardware in the loop will fail. So we used a real-time patched Linux kernel here in this case, and also an OS allows you that you conveniently can access to it via an Ethernet controller and stuff like that, and do the model cross compilation on a normal lab computer, and then just send the executable down to the hardware board. Yeah, and we used a set board. It has a SoC in the middle. It's a Swing 7020. It has a quite large FPGA and a dual ARM A9 with 660 megahertz. The ESD card holds the operating system we just talked to. The FMC connector is quite convenient to connect to the external hardware. And there's where the flyback converter will connect to. Important to notice is also that the processor and the FPGA are tightly coupled with an XI bus, and directly gain access to the level 1 caches from the processor from the FPGA, so you can transfer data fast forth and back from the FPGA to the processor. And the Ethernet, as said earlier, is used to couple to the controlling lab computer, where COSEDA did the compiling for the test bench. And it is really cost effective compared to the DSpace world, because the set board comes around below $500. And there are even other sync device boards like the Snickerdoodle board and stuff like that, which are in the same price range. Yeah. To give an overview what the sync devices we are looking at, so we are here in the cost optimized device, the highest cost optimized device. If you go to the mid-range devices, you get larger FPGAs basically. The CPU core don't get speeded up as much as the FPGA, but they are available in 3 different speed grades, where the set board is the lowest speed grade with 666 megahertz, and there are sync devices available up to 1 gigahertz here. You can also see that there are 85,000 logic cells. I'm not in the NXP use case. We didn't use them at all. So, or we used only a portion of it. So there was no need to go for a bigger board here.
Okay, thanks for that. Then let's move into the last part of the presentation on the demonstration and the application. So I already mentioned the power electronics application. You see here a more detailed diagram how that looks like. And we also took a photograph on the lab. And here again, you see the Z board as well as the application board, where we have the external interfaces, like the gate driver, as well as the AD converters to interact with the external world. Measurements and simulation results. Here, I think you see at the left-hand side, you see the measurements done on the Z board. and the simulation results at the right side using the System C AMS models. And we were really happy to see that we have a very good equivalence, correspondence between the simulation world and the measurement world. And so let's follow a few signals. So we, for instance, here in yellow, the MOSFET drain voltage, which is actually where we start detecting the valley. So you see here the signal going down is following, let's say, sinusoidal signal, and at its minimum, we really detect what we call the valley. And at that moment, we switch on the gate, which is the signal here in green, and then the MOSFET. We measure the current through the MOSFET. The so-called conducting phase, and that current rises linearly because of the filter, and before it will switch off. And this whole system achieves a balance so that the exact amount of energy transferred to the secondary side delivers a specified value. So in our case, 3 ampere at 12 volt output. And what was also very nice to see is that some imperfections we have in the system due to the components we use, that they also show up in the they show up in the, of course, in the real life, but we also have those type of imperfections also in the simulation model. So some ringing you see when components switch on and off, they are also there. So really good comparison was possible. And I think it's good to notice that here in the background, in the measurement environment, we actually run some stuff in on the ARM A9 processor and running simulations, right? So one of the challenges, I forgot to say that, but as part of the hardware in the loop, you see that we have signals going into the chip and going out of the chip, meaning that the interaction between the application and the device under test is really requiring that we meeting real-time constraints. It would be much easier to decouple those two worlds, that you, for instance, your test bench and your DOT, you decouple it and then you have less stringent time requirements. But in this specific application, we really were looking to, okay, where is the limit to meet real-time constraints? That brings me to the summary and conclusions of our talk. So we were able to successfully demonstrate the model and hardware in the loop approach using a rather cost-effective Z board using the Sync 7000 processor, where we basically use the processor to run the mixed signal capabilities, and we use the FPGA for the digital functions. The power electronics application, our flyback controller showed that we can do this type of closed loops measurements in real time. We had a very good match between measurement and simulation results. But as already said, you really need to take special care when you develop the board, but also do the selection of your processor, finding out how many gates you need, as well as the real-time operating system constraints, whether you can really meet your real-time requirements. So in this case, we had to, of course, scale down in a few areas, which might require that for more demanding applications, you also need to have a more demanding hardware prototype environment. I think that concludes the talk. We have some references in the presentation as well as in the paper. In the paper, you will find more information. So I'm open to receive any questions.
So thanks, Martin. Thanks, Paul. So I will start talking then. Still open for questions. I see a question in the chat. And that says, is the data processing in CPU synchronized with the logic part of the FPGA? And if so, what kind of data rate could it achieve?
Paul, I think this one is for you.
Yeah, they're synchronized, and it's an analog signal, so we are not only talking about the frequency. The frequency of the signal was supposed to be 10 kilohertz, but you have to have a phase shift of 2 degrees allowed. But I think we did not meet this requirement, so we scaled down the application. So I'm not sure what the final application did for the closed loop. So the closed loop, I think, had around 120 microseconds to calculate the next step. Probably this sums it up pretty good.
Yes, the limitation is not the data rate, it's a turnaround time.
Yes.
The data rate can be quite high for the interfaces, but the turnaround time is limiting the whole closed loop application.
Yes.
So in this case, we achieved around 120 microseconds with the CPU load. If the process gets, or the system C process gets more heavy, then the loop time also increases. But if the model gets smaller, then it also gets faster. Does it answer the question? Probably, yes. Okay.
Okay, in view of time, yeah, I still a couple of minutes at the beginning of the presentation, so we might have one more question. If there are no other questions, then we continue. And it seems like we continue. So Paul and Martin, thanks a lot. I found it very interesting. Good question and the presentation. So thanks again.
Okay, bye guys.
Thanks.
The next presentation will be about accelerated coverage closure utilizing a local structure RTL code. And it will be presented by Rhys, Buggy. So I hope that I pronounce it well. You're in the meeting?
Yeah, hi.
Hi. So yeah, I would like to give the floor to you.
Sure, thank you. Okay, I'm sharing my slides.
Yeah, I see them and I can hear you. So
great, thank you. So just to introduce myself, my name is Rhys Buggy. I'm an engineer with Qualcomm Technologies in Ireland, and today I'd like to present on behalf of my colleagues in Qualcomm a work conducted in Qualcomm regarding the acceleration of coverage closure. So I guess this is something which is undoubtedly known to almost all DV teams and probably everyone in the room, and it's an area of constant development. So in this work, we'd like to present a methodology to utilize the RTL structure in an effort to accelerate this process of coverage closure. So firstly, I guess just to touch on the structure of this presentation, kind of cover what's similar in the paper. So I'd like to cover our approach, or how we define the problem and approach the problem, our methodology, and how we chose to integrate this methodology into a real-world test bench, and the use case of the RTL structure in this formulation. Finally, I guess we can close with some considerations of this approach and its potential for further work. So without further ado, I guess we can start with what is the motivation of this work. So again, this problem is is very widespread and covers a lot of different applications. So I guess general industry trends, are pointing to sort of ever larger and more complex designs and duties, which require ever increasing DV efforts. These efforts, manifest as more tests and more sequences, which in turn require more man hours and more compute resources to complete. A very high-level illustration of this coverage closure process is described on the figure on the left here, or on the right here, apologies. So here, a common approach of using random test cases or random stimulus is used to close coverage. So this is represented in cumulative coverage on the y-axis and tests or time on the x-axis. Random testing often produces a line as shown with a steep increase of initial coverage, with the last 10% or the last piece of coverage being the hardest and longest to hit. This is an often seen trend in random stimulus generation. Directed stimulus is defined, to target specific coverage or coverage goals, And when used appropriately, this can hit coverage faster, as there tends to be less redundancy in test cases. So goal is to accelerate this process using better directed stimulus from a random approach. So our approach in this case is the use of directed random stimulus. So this is using the UVM constrained random stimulus generation, directing this as required. So really this is building on top of constrained random testing. Something that we define here is direct random stimulus. And this provides an approach to utilize random or generic test cases and stimulus generation to better target coverage requirements. And this is sort of what we're aiming for, I guess, in the green line, ideally. So to aid in defining a problem statement, we first define a baseline approach. So this is representative of common DV processes. So this is illustrated, I guess, in the center here, as running simulation or regressions, whereby input stimulus or UVM transactions are simulated on DUT with resulting coverage being analyzed by the DV engineer. To address coverage holes, I guess two broad approaches can be taken. So one is the random approach, using UVM constrained random stimulus generation. However, like this can be difficult to hit specific requirements reliably, requiring multiple reseeding, and the results can be overdefined, negating the purpose of random testing in the first place. The second is directed approach, or manual sequence definition, requiring the writing of specific test cases and sequences. However, this approach can be time-consuming and difficult to manage, as in it can result in redundant test cases and quite a bloated test list. So if random test cases are defined from this, we can ask, can random selection be augmented to better direct coverage closure? Or put simply, can we do directed random stimulus, as we discussed in the previous slide? So moving towards this, a naive formulation or approach from this baseline is to direct the prediction of coverage outcomes. So this would be generating a mapping of input stimulus to coverage outcomes. This approach has been explored before with varying results based on its particular use case. As an overview, this approach is demonstrated to be suitable for simple coverage definitions. That is, coverage with a well-defined or simple mapping from input stimulus to output coverage. This means it's suitable for simple coverage, input functional coverage, simple DUT coverage. However, it's broadly not suitable for more complex types, for example, combinatorial or sequential coverage types. This can also include complex or state-dependent DT coverage and can be hampered by large input spaces, which may constitute many different interfaces or types. All of this can be difficult to manage with this formulation. So one approach to improve upon this is to incorporate RTL structure. This is, I guess, where the RTL or DUT behavior can help in the prediction of this mapping. And using this mapping can drive stimulus to desired coverage outcomes. So this links back to the title, I guess, of our paper, and it's how we can incorporate the structure of the RTL to describe DUT behavior. And this approach is what we'll describe further in this work. So as discussed, the generic baseline approach involves generating input stimulus, UVM or otherwise, simulating on DUT, and recording coverage and traces for evaluation. This evaluation is typically conducted by the DV engineer to facilitate defining new input stimulus and reseeding test cases for the next regression. For coverage purposes, this often means running many random tests with a significant amount of redundancy. Again, I'm sure this is a pretty common state of affairs. So at an overview, on the slide here on the bottom, our approach aims to augment this approach, or augment this. So at a high level, this means to instrument a feedback and evaluation of stimulus with respect to coverage goals. In effect, trying to create a feedback loop which provides some level of automation. In this method, input stimulus or transactional stimulus And for the purpose of this presentation, we'll kind of use transactions and input stimulus interchangeably. The input stimulus is simulated for a specific period of simulation time. After simulation, this can be evaluated as to its contribution to coverage, which is aided by the RTL structure or description of RTL structure, which is represented here in the middle by our graph. And this graph is descriptive of the RTL structure and therefore of DUT behavior. With respect to coverage, this graph describes the relationship of signals to signals and signals to cover points within RTL. This provides a scoring mechanism for input stimulus to map to coverage goals. With this evaluation, we aim to construct a method to generate a feedback loop to direct stimulus generation. And this stimulus generation is aimed to be best suited to our specific coverage goals. So with this evaluation feedback mechanism in mind, we'll further discuss then the generation and role of the, we'll further discuss the RTL and the structure of this graph later in the slides, become a bit clearer. Well, firstly, just take a quick look at the implementation and how this fits together. So the approach discussed on the previous slide was applied to a UVM test bench using a standard system Verilog, UVM framework, and methodology. So starting in the UVM sequence, the sequence items were parameterized using system Verilog constraints. So this provided a way to direct random sequences by overriding these constraints. And this is building on top of our random constraint. This approach, I guess, has the benefit of being simple and quite generic, and allows us to target a wide range of test benches and contexts. These parameters were then accessible from a Python environment using a system Verilog Python bridge, and enable these parameters to be easily updated and modified during simulation. The directed stimulus can be simulated on the RTL or DUT, and coverage is collected via sampling in a time interval fashion. So this is using the traces as in the previous slide. A model can then be used to map the input stimulus to coverage outcomes and close the loop for evaluation feedback. That is, to map input stimulus to coverage outcomes. And this is our place here. So within the Python environment, many applicable models could be chosen. And for this purpose, a genetic algorithm was chosen. So this model is chosen to search the input transaction space for our best or most suitable stimulus from a random test case. So using this framework, we could instrument directed random stimulus. So the reasoning for the genetic algorithm model choice is to search a large input space for best stimulus. So using the test bench integration as previously described, and the transaction space can be explored as defined by UVM transaction items. In this way, we aim to use search and evaluation methodology to select these transaction items. This iterative search and evaluation method is described here on the left-hand side. So this entails, I guess, setting the transaction parameters or what we want our stimulus to be, simulating on DUT, parsing the outcome and then scoring these transactions related to their covered outcomes, updating our known transactions, which are good, or updating these scores to our transactions, and then continuing on in an iterative fashion to evaluate a set of transactions, which we know from the input space. So the use of this approach allows for input stimulus to be directed to favorable RTL states or coverage goals by implementing this iterative exploration. And this approach is what's implemented by the genetic algorithm. So with that in mind, I guess it's worth touching on why use a genetic algorithm and what is it. So the genetic algorithm was selected to be used as a search-based technique suitable to searching the input transaction space. So what is it specifically? It's an optimization algorithm, which is best suited to difficult problems, such as the complex space of a transaction or test stimulus space. This is particularly important where only near optimal solutions may be found. Of particular benefit is its ability to operate in large search spaces while being computationally efficient. So this is especially useful in the context of the input transaction space, as this can easily grow very quickly depending on a test bench configuration. An example use case of this, which we saw, would be say 10+ buses, each of 20 to 30 parameters each. So the growth in the parameter space can prove very challenging for some optimization algorithms. So to give just a brief overview then of how the GA model operates and how it sits in our context, on the right-hand side here is just a brief description. So the algorithm selects from initial population as defined from a given input space. So in this case, our transaction space. A subset is chosen from a known scored population, in this case by means of coverage scoring. A search is then implemented through small or random perturbations of these transaction parameters. These are then run and simulated to find the scores, and those best scores are returned to the population for further iteration. And this instruments this iterative search, which aims to both explore and exploit the input space. So stitching this into our framework, this provided us with a model which was capable of dealing with a large input space, compatible with our scoring feedback mechanism, and suited to finding near optimal solutions within the random stimulus framework. So all this brings us to the RTL graph and this methodology and how it fits into our format. We discussed the framework and integration, and here we can see how RTL and the RTL structure can be utilized within this framework. As mentioned previously, the RTL structure was utilized to get a description of the relationships of signals to signals and signals to cover points. This structure helps to provide a better scoring mechanism for a given transaction with respect to a cover point or coverage goal. More complex cover points can therefore be targeted with stimulus with aid of this graph description. And this sort of general graph description is showed here in the top box. So this was implemented with a tool developed to parse RTL to a graph structure, with this graph structure being descriptive of these signal relationships. This can also then be included to only look at subgraphs, so smaller parts of this graph, which may be a better use for target coverage or coverage purposes. This graph is descriptive of RTL and therefore DUT behavior. So this description is useful to derive a score more illustrative of expected coverage outcomes, where these coverage outcomes are dependent on DUT behavior. So this is modeled using windowed signal statistics, and this is represented on the bottom box down here. So these statistics are used with the graph to model the DUT and coverage behavior for a given input stimulus or a transaction. And this data can then be used to iteratively direct input stimulus. So all this is to say is that this RTL graph gives us a better idea of what our input stimulus and what its effect is going to be. So using the RTL as part of stimulus evaluation provides a more descriptive data, otherwise not available in generic simulation runs. So from this, we can take a quick look at results. So as described, I guess, to this point, the methodology is quite versatile, as it can be incorporated into UVM test benches using random test cases. To evaluate this, test IPs for IP test benches were selected from existing use cases, with these being representative of real-world test benches and RTL use cases, RTL structures. For evaluation purposes, 2 IPs were selected with contrasting characteristics. These test IP were selected to cover a range of scales, where the first, IP1 on the left, had 50,000 gates. The second, IP2, had 400,000. They were also selected to cover a range of cover point distributions. So this distribution, as we define it, is the probability of a given cover point being hit from a random test case. And this distribution for these IPs range from 1 in 100,000 to 1 in 100. So this provides a wide range of sizes and also cover point characteristics. In the results shown, cumulative coverage is plotted on the y-axis with simulation windows on the x-axis. The x-axis being simulation effort. In IP1, on the left-hand side, the blue line represents a baseline random test, so typically reseeded to hit these coverage goals. Presented in the red line is our methodology using the genetic algorithm, or GA, to direct random stimulus. This IP represents a distribution of rare coverage goals, that is, coverage hard to hit and requiring significant random testing. The GA can be seen to hit initial coverage much faster than purely random, with close to the same coverage and a significant 44x in simulation saving. In the second example, IP2 on the right, the blue line again represents a purely random test, typically reseeded to hit this coverage. This IP has a less pronounced rare distribution, as seen here in the number of the effort required on the x-axis. And presented in the red line, the GA can be seen to hit initial coverage faster and reduce the effort to hit this the hardest bit, or the last 10% of coverage, as seen here with a 25x simulation saving. So these results on real-world IP, I guess, illustrate the ability of this methodology to reduce redundancy in random testing and achieve significant savings for these coverage goals. So I guess some considerations then, which are worth noting. So with this methodology in mind, it's worth noting some considerations using this approach. So this methodology and overall approach has some limitations. These are worth noting, specifically as they pertain to test bench integration, IP selection for use, and coverage types. And these all affect the performance of this approach. So the windowed approach of data collection, how data is collected, can be noisy, as it's difficult to make each window fully independent. Initial starting DUT states and sequential effects introduce noise into the collected data, affecting our performance. These can be controlled, but at the moment it's quite a manual process. Input transaction parameter search spaces can be quite difficult to define and difficult to manage. So this is dependent on TB structure, but typical UVM transactions have a complex and parameterized search space, and extrapolating the search space is a non-trivial task. The use of RTL structure is well suited to code coverage types, but is difficult to expand to other coverage types where the RTL structure and coverage related impacts may be difficult to model. In addition, this approach doesn't consider if the search space is insufficient to achieve coverage. And so never hit coverage is a challenge to identify as being hittable under this scheme. So again, this is trying to use existing random test cases, or random test cases developed for this purpose. So with these in mind, some further work worth mentioning. This approach showed positive results, and potential further work might include developing a score to consider the transitioning between different input parameters. Capturing this would aid in reaching more complex DUT states, which affects or may improve performance for more complex coverage types. Also, creating a process to identify and structure a valid input parameter space will be useful for coverage closure. And in addition, to expand the approach to additional coverage types as may be of better use to DV teams. So in summary, this approach as presented is good in getting to intermediate levels of coverage faster. So this is observed as a 25x speed up in hitting such target coverage. And again, faster initial coverage closure reduces required compute and provides more sync time to DV teams for TB developments and perhaps running more useful simulations. This approach targets rare coverage. So rare coverage is here characterized as having coverage points with a low probability of being hit. And this example was observed in a 44x speedup in hitting this type of coverage. Achieving this coverage earlier in the regression cycle is beneficial in saving random testing time by reducing redundancy in reseeding. And this is, I guess, a key point. And this also potentially promotes more diverse stimulus, with increased potential for finding bugs or design problems. This approach is also flexible. So using a Python system Verilog bridge, common machine learning models and libraries can easily be implemented. So directing stimulus using system Verilog constraints is a common to many UVM or transaction-based test benches. And the ability to direct in simulation facilitates the use of existing random test cases. And finally, I guess to close, this methodology makes efficient use of random test cases for coverage closure. So that is, I guess, to allow generic random tests to be better utilized in simulation time. So rather than just reseeding, they can be used perhaps slightly more intelligently. Facilitating the use of stimulus search in a defined input space generally promotes more diverse stimulus and faster coverage closure, or at least that's what we've seen in our examples. Targeting rare coverage is likely to drive stimulus to less common states and may see additional benefits to the verification cycle. So thank you for listening. I hope this presentation was interesting. And I'll pass back to the moderator.
Thanks, Rhys. Let's go on to the questions. From my point of view, that was very interesting presentation. I also have questions, but I would like, let's say, to give the opportunity to other people. So if somebody has a question, please drop them. And I see a question in the chat. So let's start with that one, and that is, what cover point models did you use? Is it linear distribution power or of two intervals? Question mark.
Sorry, coverage models.
What cover point models? That's what's stated in the chat.
Cover points. So for these purposes, we're mainly looking at code coverage. So we're looking at sort of toggle coverage of the RTL.
Is that the question, or
am I answering the question?
No, yeah, that's not my question. So I'm just asking for feedback. Yeah. Okay, I guess so. Yeah, we still have a bit of time. I have a practical question, basically, and that is about the Python system Verilog interface that you mentioned. Is this, let's say, a direct relation, or do you have to use an additional language? For example, Python C and then C to system Verilog?
Yeah, so we're using a library called PyVPI, which I guess is it's implemented similarly to the system C, like DPI, but I guess it kind of just works for Python. And I guess the benefits of this is that we could just use Python models, I guess the Python language, which is easier to use with machine learning libraries, and directly interact with system Verilog variables.
Meantime, we also have, let's say, another question in the chat. The question is, can you share an example of a simple graph model generated from an RTL code?
Sorry, I didn't catch that. A simple
graph model generated from an RTL code.
Okay, sorry. Sorry, actually, I can't see the chat on my side.
Okay.
Sorry, could you repeat the question? Is to share a graph model?
Yeah, so maybe it would be good, let's say, to elaborate a bit more on the process of creating the graph from the RTL, like what you discussed in one of your earlier slides?
Sure. Yeah, so there was a tool, I guess, developed within Qualcomm, which generates this graph structure from the RTL code. So from the RTL, the RTL is parsed to create a graphical representation of the signals within the RTL. I think that's all we have for the scope of the presentation.
Would it be then some kind of state space, this graph model? Should I see it like that?
So it represents the structure of RTL. So it's not related to like any specific state space or FSM, say, states that might be within an RTL. It's more general description.
Okay, thanks.
Okay, great, thank you.
Got to the end of this session. Thanks a lot, Rhys. It was a very interesting presentation, also on a very relevant topic. So that is also something want to mention. So thanks again. Yeah, the only thing that I have left for this session is, before closing it, is to mention that we should not forget to vote for the best paper and the best poster award. And there's a link supplied in the chat to do that. So thanks everybody for attending, and yeah, I think that it was a very useful and insightful session today. So thanks a lot, and enjoy the rest of the conference.